problem. We used optimization for solving logistic problems. In many other situations, we use optimizations. So, which is a very powerful mathematical tool and which can be used here also. So, before starting the task, let me share the slides and then okay. So, okay, so we'll start with the PID controller tuning using optimization as well as the frequency response method. As I told you, optimization methods is a very powerful tool for design of controllers, not only for design of controller, for many other problem solving aspects. Conceptually, the optimization method is pretty simple. Formulation of optimization problem is not so difficult, but getting the proper solution is not a trivial issue. Normally, for controller tuning, what we can do is we can specify a controller structure with few parameters. Here I am talking of controller structure which may be PID or may not be a PID. Any type of controller structure I can specify with some parameters. These specifications are expressed as inequalities functions of the parameters. So here basically for a controller tuning we can have number of specifications like specifications of integral error criteria, specifications of overshoot, specifications of decay ratio, specifications of rise time or response time. You can have specifications in the frequency domain as gain margin or phase margin. So we can devise number of specifications for controller tuning, and one of the specifications which we think is the most important one, we use this one as an objective function to optimize. And other specifications can be used as the inequalities or equalities functions of the parameters. This method is well suited and it is used heavily for PID controller tuning because in PID controller we have the defined control structure as well as the parameters are known. I'm not talking of the parameter values, but the number of parameters are known. So before going to that, just let me just give you a brief introduction to the optimization problem. How do we formulate an optimization problem? And in optimization problem, there are three ingredients. One is the objective function. Second one is the equality constant, and third one is the inequality constants. This equality constant and inequality constants are coming from the process model. And the objective function is the economic model, which basically we want to minimize. So mathematically, we can formulate an optimization problem as minimization of fxy, where fxy is the objective function and it is always to be a scalar quantity. So fxy is an objective function subject to hxy, which is an equality constant, can be a model equations, and gxy less than or equals to 0 can be specifications. So process specifications. Here x and y can be a continuous variable, can be a discrete variables, or maybe a combination of both continuous and discrete variables. So this way the optimization problem are formulated. So in an optimization problem, you should remember there are three ingredients. One is the objective functions, which we have to minimize or maximize, and the constraint, or we can say the subject to equality constant and inequality constant. So we have to specify inequality and equality constant. When we are specifying the equality constants, it should be such that we should have enough degrees of freedom, at least 1 degree of freedom available to us. We should have at least 1 degree of freedom available to us to have an optimization problem. If hxy is equal to 0 has your number of degrees of freedom is 0, which means your number of variables and number of equations are same, then we can solve hxy 0 and get the x and y variables. So there is no optimization involved in this. You have to have a number of variables more than the number of equations so that you can play with the number of degrees of freedom or the unknown variables to minimize certain objective functions. So this is an important thing that when we will do formulate an optimization problem, we should remember this thing. Okay. So let's move to the control problem. Now in optimization methods of controller tuning, the most used objective function is the integral error minimization. So normally we do an integral error minimization. Here error means y set point minus measured variable or y response. There are 3 types of integral error normally considered. One is the integral of the absolute value of the error. Second one is the integral of the squared error. And third one is the integral of the time-weighted absolute error. Normally we use the time-weighted absolute error or time-weighted square error to take into account the system where the system response is sluggish. So for a control problem, we can formulate as minimize phi, that phi can be IAE or IAC or ITAE subject to this equation YS is equal to GS GCS 1 plus GS GCS YSPS plus GDS 1 plus GS GCS DS. And GCS is equal to KC 1 plus 1 by tau IS plus tau DS. So we will have 2 equality constants over here to solve this problem. And in the GC we have got 3 parameters KC, tau I and tau D. So knowing the parameters of G, and the YSPS and DS, we can minimize IE, IAE, IAC or ITAE to get the values of KC, tau I and tau D. Here you can see we have got 2 equations and 3 unknowns. So we have got 1 degree of freedom which we can utilize to minimize the phi. In this problem formulations, we have used a linear equation that YS is equal to YS some GPS into YSPS plus GDS into DS is a linear equations. Instead of these linear equations, we can use a nonlinear process models also. So we can use a nonlinear process model over here with the PID controller, and we can formulate the same problem again for minimizing the IAE, IAC or ITAE. Okay, so let's take one example. Let's say GS is equal to first order with date time model. Before that, let's most of the cases here, if I take a first order with date time model, then you will find in the literature there are a number of research results. There are a number of research results where people have done the optimization based on the first order date time model and the PID controller. And based on the result, they have developed tuning relationships which are based on set point tracking and disturbance rejections. These tuning relations are normally of this type: P is equal to A into theta by tau to the B. Theta is the date time, tau is the time constant, where P is the specific controller parameter and A are B and constant, like Kc is equal to A into theta by tau into B to the power B. Normally, these correlations are developed for theta by tau ranging from 0.2 to 0.8. Normally, these tuning relations are valid for theta by tau ranging from 0.2 to 0.8. I'm just giving you some data over here, tuning relations from the literature. In any standard book, you will get these tuning relations. Like here, you can see. Like here, you can see for a first order with date time model, we have developed the PI parameters based on this and the PID based on this. Similarly, for a set point tracking, PI is developed like this, and PID, we have got the tuning parameters like this. And this here, the design relationship is y is equal to A theta by tau to the power B. So if you, where y is equal to k into kc for a proportional mode, for the integral mode tau by tau I, and for derivative mode tau d by tau. So based on this, these equations are developed, and these are basically A and B coefficients for these equations. And for set point changes, the design relations for the integral mode is tau by tau I is equal to A plus B theta by tau. So this way we can get the PID parameters using the ITA performance index. But for your process also, you can do it yourselves, the controller tuning. Here, basically, I will give you one example for that, how we can do it, in the MATLAB Simulink model. So let me discuss the one MATLAB Simulink implementation of developing a PID tuning parameter using optimization technique. So in MATLAB Simulink implementation, what we can do is we can create a Simulink model of feedback control structure with the process and the PID controller. So this is basically the Simulink model which I have developed in the MATLAB Simulink environment. I have used a process over here. It's not a first order with date time, but I have used a process with 1 by s plus 1 to the power 4. And I have used a PID controller. When I'm devising the PID over here, I put the PID parameters as a variable. Like I put PID parameters as Kc, tau I, and tau d, without assigning any value to these variables. And I put a certain step change in the set point. I put a certain step change in the set point, maybe a unit change in the step change in the set point, and I record the error over here. I took absolute values of the error and then I integrate. And this cumulative error is saved over here. So the error value is saved over in the workspace, as well as the output response is saved in the workspace. And before saving, I run this Simulink model, putting some specific values of Kc, tau n, and tau d to find out what is the normally time required to settle. Right. So accordingly, I put the total simulation time. Accordingly, I put the total simulation time. So then I save this Simulink model. I save the Simulink model. Here I have used the integral absolute error performance criteria, and then which is basically represented by this error variable. And then I save this Simulink model with some name, let's say C5.SLX. Okay. Once I save the Simulink model, then I go to the MATLAB environment. In the MATLAB, I create a MATLAB function script. And in this MATLAB function script, I write this function. In the MATLAB function script, I write this function. This function basically gives me the objective function. This function is basically the objective function. So I calculate the objective function over here. Here you can see this statement assign in is basically assigning the values of the Kc by x1, x2, and x3. These x1, x2, x3 are the variables which are used by the optimization algorithm. So I'm specifying x1 as a Kc, x2 as Ti, and x3 as Td. This Kc, Ti, and Td is specified over here in the PID. I put the control parameters, PID parameters as Kc, Ti, and Td. So this I am assigning this Kc as x1, Ti as x2, and Td as x3. Then I am simulating this Simulink model. I have saved the Simulink model as C5.SLX. So using this command, I am simulating this Simulink model. The output of the Simulink model will be SIMOUT, which is a structured variable. The SIMOUT contains both error as well as y. So I take the SIMOUT.error, and this error is a cumulative variable. So the last value of the error normally I take. So end is basically referencing to reference to the last value of the error in the error array. So I am taking the last value of the error array, which SIMOUT.error, which is, since SIMOUT is a structure variable, so I am accessing the error variable as the SIMOUT.error, and I am considering only the last value of that error. So I am putting end over here. So that is basically my IAE. So this functions gives me the objective functions, IAE. So once I write these functions, I save this function, and I save the file. The file name should be the function name. So here I'll save this as opt_c5.am. The file name should be opt_c5.am. Okay. Now in the MATLAB command window, I use the routing fmin search. There are other routings also. I use the routing fmin search to find the optimum PID parameter. So in this fmin search routing, we require an initial guess value. So I give an initial guess value x0 as PID as proportional controllers as 0.1, and other values as 0 and 0. So normally you give this very small values of proportional gain and others as 0, and then you start searching the Kc, tau n, and tau d. So if you give this value, then you'll get x output in the x. You'll get x1, x2, and x3, which are basically Kc, tau n, and tau d. So this is basically a MATLAB and Simulink implementation to find out the Kc, tau n, and tau d for a specific system. Okay. The advantage of this method is, instead of 1/s, this basically I am using a linear process model. Instead of this, I can use a nonlinear process model. I can use a nonlinear process model over here, and still I can use this same implementation to find out the Kc, tau I, and tau d. That is an advantage over here. Is it clear to you? Before I proceed further, let me just get your feedback. Is it clear to you?
Sir, what is base in assign-in?
Base means it's a workspace. Basically, I am telling in the workspace there is a value kc. What happens is in the Simulink model, I have put the value. I have put a variable in the PID parameters as kc, tau I, and tau d. I have not given a specific values. Okay, I put it as a kc, tau I, and tau d. Now this kc, tau I, and tau d, when I am assigning that the kc should be same as kx1, tau I should be same as x2, and tau d should be same as x3. This one will be there as in the MATLAB workspace. So when I am running this simulation C5 model, when I'm simulating this C5 model will look for kc, tau I, and tau d. So automatically it will take kc as x1, tau I as x2, and tau d as x3. And when I'm initializing this, I am also telling that this x1, x2, x3, initially it's x0. That means 0.1, 0, and 0. So it will start from here that x1, x2, x3 will be 0.1, 0, 0, which will be assigned as kc, tau I, and tau d, and then it will be simulated. Then it will go to the fmin search. New values of x will come, and this way the process will go on till this IA is minimized.
Yes, sir, understood.
Okay.
Sir, this minimization was for servo response. Can we do it for both together? Like
you can do it for both together.
okay.
Yes, you can do it for this is for servo response. You can do it for both together. Okay, so if you have to do it for both together, then in that case, what you have to do is you have to give step response to the for both disturbances as well as the set point.
Yes, sir.
If you do that, then you can do it for both together. So there is no limitations on this that it has to be done for the servo or it has to be done for the regulatory problem. You can use both the problems simultaneously or sequentially.
Okay, sir.
Okay. Okay. Now let us move to the next. So this is basically the optimization technique using MATLAB Simulink. So any kind of process model you can use, and we have used here the PID here, but instead of PID, we can use any type of controller equations, which can be an unconventional controller equations also, which may not be a PID, may be some other functions or ratio of polynomials in S. Okay. Now, if you look at the controller tune, compare the controller tuning relationships. If you look at the here the controller tuning relations, not only I am talking of the IAE. If you look at the controller tuning relations for the Ziegler-Nichols controller tuning relations, if you look at the Cohen-Kuhn controller relations, if you look at the CHR controller tuning relations, in all types of these controller tuning relations, you'll find these 4 points. The first point is the controller gain kc should be inversely proportional to the product of the other gains of the feedback loop or the process gain. I say so the kc will be inversely proportional to the 1 by k. Kc should decrease as theta by tau, that the ratio of the time delay to the dominant time constant increases. Which means when the dead time increases, kc has to decrease. In general, the quality of the control decreases as theta by tau increases, owing to the longer settling times and larger maximum deviations from the set point. Both tau I and tau d should increase as theta by tau increases. For many controller tuning relations, the ratio tau d by tau I is between 0.1 and 0.3. So as a rule of thumb, we use tau d by tau I as 0.25 as the first case. What happens is in some of the cases, in some of the cases you will find your specification is such that you can have only two variables. You can have only two variables, two unknown variables. Now, if you have two unknown variables, then you can solve only the PI controllers. Then how do I get the derivative time constant? So normally the derivative time constant we find out by using this relation tau d by tau I is equal to 0.25. And so we get the tau d values, then we implement the controller and see the response. And accordingly, we change this tau d by tau I from 0.25 to, let's say, we can reduce to 0.2, or sometimes we increase to 0.3 and so on. Fourth point is when integral control action is added to a proportional only controller, Kc should be reduced. The further addition of derivative actions allows Kc to be increased to a value greater than that for the proportional only controller. This you can easily see for the Ziegler-Nichols tuning technique. If you look at the Ziegler-Nichols tuning technique, you will find the Kc value is minimum when you are using only PI controller. The tuning relations for PI controller, Kc value is minimum, and the Kc value is maximum in case of a PID controller. Now I will discuss is the frequency response technique for the controller design. I will use two techniques over here, one based on the gain margin and phase margin, which is in a way, let's say, Bode plot, and another technique I will use using the Nyquist plot. Although both Bode and Nyquist plot are basically related. So if we start with the based on the gain margin and phase margin specifications, we know the gain margin and phase margin are normally used to make the controller more robust. Robustness, basically the definition of the robustness is the ability of a controller to take care of the estimation error of the process model. All these controllers are designed based on the process models. So when you are estimating a process model, there can be error in the gain, there can be error in the time, estimation error in the integral time constant or derivative, I'll not say integral time constant, process time constant or the process delay. So gain margin and phase margin basically used to take care of these estimation errors in the process parameters. Also, the phase margin is related to the damping of the system. So the more damp in the system, the sluggish will be the response, but also the robustness of the controller will also increase. So for phase margin, if I increase the phase margin, the damping of the system will also increase. Now, if we consider the process transfer function GS and the controller transfer function as GCS, then from the definition of the gain margin and the phase margin, we can write these four equations. One is the definition of the phase crossover frequency. The phase crossover frequency is where the angle of this open loop transfer function G into GC is minus 180 degree or minus pi. So this is one equation, the argument of G j omega P into GC j omega P, which is the G open loop, is equal to minus pi. The gain margin is basically the difference in gain when at phase crossover frequency. The difference in gain at phase crossover frequency, the difference in gain from the unity. So in this case, AM will be 1 by modulus of G j omega P, GC j omega P, where omega p is the phase crossover frequency. At gain crossover frequency, the amplitude AM is equals to 1. At gain crossover frequency, the amplitude ratio should be equals to 1. So that way the gain crossover frequency is defined. So I write these equations over here, where omega g is the gain crossover frequency. So at gain crossover frequency, amplitude of the GOL, open loop transfer function, is equals to 1, which basically definitions of the gain crossover frequency. And the phase margin, which is calculated on gain crossover frequency. So at gain crossover frequency, phase margin is the argument of this GOL at gain crossover frequency plus pi. So the difference between the pi of the minus 180 degree and the angle of the gain angle of the G open loop at the gain crossover frequency. So these are the 4 equations, 2 equations for the definitions of gain margin and phase margin, and 2 equations are definitions for the phase crossover frequency and the gain crossover frequency. Now in these 4 equations, in these 4 equations, now you can see the G parameter is known, but in here in the GC parameter, in the GC, if I use a PID controller, then we have got Kc, tau I, and tau d. 3 parameters are there: Kc, tau I, and tau d. Okay. So we also here we do not know what is the omega p or the phase crossover frequency. Also, we do not know what is the omega g, the gain crossover frequency. So we have got 4 equations and 5 unknowns over here. 4 equations and the 5 unknowns over here. So these equations we cannot solve directly for a PID controllers. Just let's say one example over here. We take the PI controller. If I take a PI controller initially, so GS will be K tau S plus 1 e to the power minus theta S, and GCS will be Kc 1 plus 1 by tau IS. So we'll have GS and GCS this expression. And if in the first equations, I can have from these expressions, I can have pi by 2 tan inverse minus omega p tau I. So the first expression is nothing but I am finding out the argument of Gj omega p, Gcj omega p is equal to minus pi. So the argument is nothing but the angles. So I am finding out this 5 by 2 plus tan inverse omega p tau I for this one, and tan inverse minus omega p tau for this one, and minus omega p theta for e to the power minus theta s. So I am writing the phase crossover frequency equations over here. Then I am writing the gain margin equations in terms of these relationships. I am writing the definitions for the gain crossover frequency, and then I am writing the equations for the phase margin. So once we have written these equations, we have got now 6 to 9. The 4 equations are here. 6 to 9, 4 equations are here, and our unknowns are omega p. The k is known to us, tau is known to us. So our unknowns are omega p, omega g, tau I, and kc. So there are 4 unknowns and the 4 equations. So I can solve it directly. I can solve this directly to get the values of Kc and tau I. If I specify AM and phi m. If I specify AM and phi m. So I specify AM and phi m, and then I find out the 4 unknown variables, which are omega p, omega g, kc, and tau I. So for a given process k, tau, and theta, and specifications am and phi m, the equation in 6 to 9 can be solved numerically for PI controller parameters kc and tau I and the crossover frequencies omega g and omega p. Now, in case of a PID controller, for this design of FODT processes, if I use the tau d, then it will make a 5 unknowns and 4 equations, which I cannot solve now. So we need another equations to solve this. The another equations we can provide if we put tau d is equal to 0.25 tau I, another equations. Then in that case, I can get a PID equations in terms of tau, in terms of tau I. So tau t I will get in terms of tau I. This is one approach of getting the PID equations using the frequency response analysis. The another approach is we can use an optimization technique. So here we can do is other approach for calculating the PID parameter is to formulate the optimization problem. Here what we can do is, before telling this, here what we can do is, say we get a tau d as relationship as 0.25 tau I. Then we get a PID equations. We implement these PID equations on the process and we see the response. And based on some other specifications on the response, we vary these relationships. So that we can get a desired response. That we can do is by trial and error method. Instead of doing this by trial and error method, we use that particular specifications to formulate an optimization problem. Like we can use an integral error as an objective functions, and we can use the equation 6 to 9 as the constant. So in that case, we do not have to use these equations. Tau d is equal to 0.25 tau I. We use these equations. So what we can do is we write minimize phi. Subject to these equations. Where phi is basically the integral absolute error. Okay. So the other approach of calculating the PID parameter is to formulate an optimization problem with integral error as the objective function and equation 6 to 9 as the constraint. The next method I can use is using the Nyquist plot. So if I take this open loop Nyquist plot over here, at this point, let's say point A, you can see the directions of the proportional action, integral actions, and the derivative actions. So if I draw a line over here, this basically radially, if you move in these directions, then it will give you a proportional actions. If the angle is increased, then it will give you integral actions in this direction, and the derivative action is in this direction. So a properly chosen kc tau n and tau d, I fix these values. For a PID control process. So for a PID control process, let's say this value is A1. So I fix a value of A1, and from this value, I can find out what should be the values of the kc tau n and tau d. Okay, so this is basically the philosophy of finding the controller parameter using the Nyquist plot. So here basically in this typical Nyquist plot for under PID control, where A1 corresponds to the figure point A. So we say for point A in the complex plane, G j omega 0 is RA. At this point, the value of frequency is omega 0, let's say. So Gj omega 0 is equal to Ra Gj omega phi plus phi a. And in this point, the Gj omega 0 at the same frequency, Gj omega 0 is equal to Rb e to the power j phi plus phi b. Okay. Now, from this point to this point, we reach through a PID controller, because this is an open loop process, it's a PID control process. So we have a PID controller, and that PID controller at frequency omega 0 is give GC will be RC is EJ phi omega phi C. If it is so, then it is obvious that this is the frequency response for the control process. So if the frequency response for the control process RB phi plus phi B should be equals to RA into RC e to the power j phi plus phi A plus phi C. From the definition of the frequency, property of the frequency response. If it is so, then RC will be given by RB by RA. So from here, we can say RC will be given by RB by RA, and the phi C will be given by phi B minus phi A. So RC is the gain for the, or the amplitude of the controller, and the phi C is the phase difference. So RC will be given by RB by RA, and phi C will be given by phi B minus phi A. So based on this above analysis, we can define a PI and PID controller. So the PI controller will be Kc will be in terms of RB and RA and phi B and phi A will be Kc will be RB cos phi B minus phi A by RA, and tau I will be given by 1 by omega 0 tan phi A minus phi B. Okay. And phi A should be greater than phi B for a positive tau I. As a special case, if we assume that the Ziegler-Nichols tuning, then the Ziegler-Nichols tuning will be basically nothing. The Ziegler-Nichols tuning has done well at the phase crossover frequency. At the phase, so at phase crossover frequency, we have got the KCU and the PU. So if you take the Ziegler-Nichols tuning parameters, these relationships we can put it in the Ziegler-Nichols tuning parameters as Kc will be Kcu Rb cos phi B, and tau I will be minus Pu twice phi tan phi B. So Pu will be twice phi omega C, and Ra will be 1 by Kcu, and phi A will be equals to 0, because this is at phase crossover frequency. So here at the Ra will be this one, at omega will be as phase crossover frequency, and here phi plus phi A will be equals to 0, because phi A will be equals to 0, then it will be j pi at phase crossover frequency. And Ra then will be 1 by Kcu. Now to get a positive tau I, that tan phi B should, cos phi B should be less than 0, which implies that the point A1 should be in the second or third quadrant. The PID parameters, the derivative parameters, so we can also find out if I use these relationships. We know omega 0 tau d minus 1 by omega 0 tau I is equal to tan phi A minus phi B, which is basically the notch frequencies. So clearly tau I and tau d are not unique over here when you are using PID controller. So to get a unique PID design, we have to use a parameter alpha tau. We have to use the relationship tau d is equal to alpha tau I. So if I use this relationship tau d is equal to alpha tau I, then we'll have a unique parameters of tau I and tau d. So we can have a tau I will be this relationship. From this, I can get the tau I will be this relationship and tau D will be alpha tau I. So based on that, I can have the Kc, tau I and tau D. For a special case of Ziegler-Nichols tuning parameters, we will have the Kc will be given by this equation, tau I will be given by this equation, and tau D will be given by this equation. Okay, so this Ziegler-Nichols tuning formula is called the modified Ziegler-Nichols tuning formula, because the values over here will be quite different, which is given by the Ziegler-Nichols when this in their tuning formula. So that's why this is also called here. Basically, we have used the basic experimental methodology of Ziegler-Nichols, because in the Ziegler-Nichols they have used the continuous cycling method to put the system in a position where the phase difference is minus 180 degree, and they have taken the period of oscillations and the amplitude of that constant amplitude oscillations. So same philosophy over here is used to find out the Ziegler-Nichols tuning formula for the PID as well as the PI. Okay, so this is another way. This is another way of finding out the controller parameter, PI or PID controller parameter. How do I get this RB and RA? How do I get this RB, RA and phi V and phi A? So the recommendations are like this. So if I implement this, then for a first order with date time process, for different phi V, we will have this kind of relationships. So as phi V increases, the response becomes slow. Okay, the response becomes, as phi V increases, the response decreases, the response becomes faster, but with oscillations. Similarly, for the RB, if I use RB, as we increase the values of RB, the oscillation will increase. At RB is equal to 0.1, this is pretty slow, pretty sluggish response. As it goes on increasing the RB, the oscillation starts creeping into the system and the oscillation will increase as you increase the RB value. So from here, we can say, empirically, we can say the phi V should be between 40 degree to 50 degree. It has been shown for many of the systems, specifically for first order with date time system, it can be seen that phi V should be between 40 degree and 50 degree. And for RB, value will be around 0.45 and phi V is 45 degrees. So RB value normally it's taken from 0.4 to 0.6. In between 0.4 to 0.6, RB value normally is taken between 0.4 to 0.6, and conservatively, many people normally takes RB as between 0.4 to 0.5, and phi V between 40 to 50 degree. Like for in this case, if I take RB as 0.45 and phi V as 45 degree, then it will be a good choice with almost no overshoot and reasonably fast response. So this way, basically, we can design the controller. We can get the Kc, tau n and tau d based on the specifications of the phi V and the RB. Based on the specifications on the phi V and the RB. So if I specify phi V and RB, then we can know the tau I and Kc, because phi A and RA is the process parameter which is already known to us. Okay, so this basically completes the PID controller tuning and more or less the review of the process control which you have learned in your undergraduate courses. So Do you have any other questions on this? So what I'll do is now in the next week, I will take a class test on this. I will take a class test. The first class test will be on next week. This class test will be on Thursday. And preferably, I'm not putting the time as Thursday time is 9 to 10, but that time will not be sufficient to take the class test. So what I am proposing is that I will take the class test in the evening. Let's say class test. Let me take the class test from 5 o'clock. If you do you have any
Sir, we
problem
have a
with that?
class.
You have a class when?
Heat transfer.
Yes, sir. On Thursday, we have a class.
Thursday 5 to 6.
5 to 6 you have a class. Thursday, let's say in the night. Do you have any problem if I take from 8 p.m. to 9 p.m. at 7:30 to 9? Or morning, what is the problem? Do you have any class from 8 o'clock?
Yes, sir. We have a master for class from 8.
You have a master transfer class from 8. Then in that case, I have to take the exam in the evening from 8 to 9:30, let's say. Because what happens is if I put at 8 to 9 1 hour, then I cannot give you the time for uploading your answer script and so on. So this class test will be for 1 hour and half an hour for the uploading and downloading operations. So let me fix the class test at night 8 to 9:30. So we'll have the class test at 8 to 9:30. OK, on Thursday.
Okay.
Sir, what will be the format if you can give an idea?
Format basically means format of what?
Sir, it will be MATLAB based or hand calculations.
It will be combination of two. Mostly hand calculation, but it will be combination of two. But if you are using MATLAB based this thing, then the MATLAB code or MATLAB command has to be also written there in your answer script.
Okay, sir.
Okay. Okay, and then since I will be taking class test on Thursday, next Thursday, so regular class from 9 to 10 will not be there on next Thursday. Okay. So in place of that, the class test will be there in the night from 8 to 9:30. Is it okay with you?
Yes, sir. It's fine.
Sir, can we do 7?
Yes, please. Any questions, please?
Sir, can we do it a bit early?
If your friends willing, I do not have any objection. If your friends are willing.
We have a class till 6, I think. So I think 1 hour will be sufficient to get out, and perhaps from 7.
So what about others? Do you agree?
I mean, I think 3 of us have a class on computational modeling of multiphase reactive flows from 6 to 7. So starting the exam at 7 would be quite difficult. From 7:30 it might be okay.
So 7:30 to 9 or 8 to 9:30. I think 8 to 9:30 is a good time. What are okay?
Yes, sir. 7:30 to 9 is fine, sir.
7:30 to 9. Okay,
Yes,
fine. If we all agree, then I can put it at 7:30 to 9.
Yes, sir.
Okay, fine. I will send a message to everybody that the class test next class test will be on 7:30 to 9 in the evening on next Thursday, and there will be no class on the next Thursday in the morning. Okay. Any other questions?
Okay.
Any other questions? Otherwise, I will end this meeting over here. Okay.